And next we'll hear from Molham Aref, who's from RelationalAI. We'll also hear from Molham later in the afternoon during the program plan sessions. So
thank you. I got volunteered twice to give talks here today, so I'm very, very happy to meet the folks that I'm meeting for the first time and reconnect with a lot of friends in the room as well. So I think I'm a little bit of a novelty in this community because I'm, helping build a company that relies very heavily on the theory community. So, okay. So for the 15 minutes we have today, I was going to just tell you a little bit about the company and some of the problems that we are trying to solve. In the afternoon, it'll be more, more of a history lesson. Okay, so I'm going to pretend you are a prospective customer. If you're a prospective customer, you're typically like someone called a chief data officer. I don't know if you know about that role in the company. He's a chief data officer, chief information officer, but chief data officer worries about the data assets for the company. And most companies, most large companies have many, many, many databases that hold lots and lots of data. It's not unusual for us to work with companies that have, like there's one company that talks publicly about having 17,500 SQL databases that have over 400 million columns of information in them, okay? And this is a company that works in a regulated industry, and if they build models that crash the economy, they need to be able to provide some, to be able to debug that by going through and understanding provenance and data and so on. I have another customer in the telecommunications industry, 180 million columns of information, okay? So chief data officer worries about the data assets, and today the trend is that if you have lots of data, you're moving it to a data cloud of some sort. These are systems like Snowflake and BigQuery that are databases designed to run on the cloud and effectively support infinitely scalable data sets and provide infinitely scalable, or effectively, I should say, infinite computing ability. Okay, so we're going to pretend you're one of those. So you're meeting RelationalAI, and I introduced us as the AI co-processor for the data cloud. Today, we're effectively focused on Snowflake as the first data cloud, but eventually we'll work with others. So we are the AI co-processor for the data cloud with relational knowledge graphs. So I typically get some head scratching going on, so I have to define some of these terms. So what do we mean by AI? AI is super overloaded, as you know. Today, for a lot of people, it tends to mean language models. 3-4 years ago, it was deep learning. I've been at this since the early 90s. In the early 90s, we called it computational intelligence or data mining or database mining. It sort of comes and goes in various hype cycles, okay? But as someone who's also spent the last 30 years or more building intelligence into enterprise decision-making, I know that whether we're building a supply chain optimization solution or credit card fraud detection or revenue management solution, I know that we need to combine lots of different modeling techniques effectively and pick the right tool for the right part of the problem, okay? So the way we define it is as a combination of different techniques needed to improve decision-making effectiveness. Analysts like Gartner have called this composite AI. They've sometimes called it neurosymbolic AI. It doesn't really matter to me. The idea is that there isn't just one technique to rule them all, and that in practice, you need to do a combination of these things, okay? So these things include graph analytics, reasoning with logic and rules, mathematical optimization, simulation, machine learning is a general bucket they threw in here, and language models. Okay, this might be suboptimal in some way. Let's not quibble over it. The idea is sort of there are different techniques, some symbolic, some sub-symbolic or statistical or probabilistic that we use to solve hard problems. And today, I will focus more on the right-hand side of this equation, and maybe next year you invite me and I can tell you more on the left-hand side. Okay, so that's what we mean by AI. What do we mean by co-processor? So this is a kind of a novel thing that we're doing in terms of sort of go-to-market, in terms of innovation, in terms of how you build a database company and take it to market. Okay, if you go search the internet, you'll probably, not probably, you'll definitely find over 800 database systems out there that have been created by a variety of academic and industrial groups. It's just a ton of databases. And people in industry really don't want to hear from a database company coming in and trying to add one more to the footprint, okay? They're chock full, they're trying to go in the other direction. They're trying to narrow things down to like, I just want to put all the data in Snowflake and be done, okay? I don't want to have to manage 800 different database systems. So the innovation here for us is that we're going to market as a co-processor for systems like Snowflake and BigQuery, okay? What that means is, it means to us three things. It means, one, we embed inside of Snowflake, okay? So we're inside the security perimeter. We follow whatever governance is in place to help people manage data in Snowflake. We also eliminate the need to manually do data synchronization. Effectively, our system shows up as a set of materialized views inside Snowflake that lets you do things that you wouldn't be able to do otherwise. So this embedded idea is very important. And usually, at this point in the conversation, the prospect goes from like, arms folded, like hurry up because I'm busy, I don't have time for you, to, perking up a little bit because they really don't want to solve these types of problems with point solutions that force them to copy the data back out of Snowflake and make it, have to replicate security, governance, data synchronization, and so on. And then copy it again to feed it to a rule-based system, and then copy it again to do mathematical optimization, and then copy it again. Like, that's not the direction they want to go in. Okay, so criteria one is being embedded. Criteria two is being cloud native. A lot of the point solutions that support these types of workloads were built in an on-premise era. They're kind of like the Hadoop of their workload, the Hadoop of graphs or the Hadoop of rules and so on. And one of the nice things about Snowflake, and the reason people picked it over Hadoop and over Teradata and Netezza and so on, is it has this really innovative cloud native architecture that gives it this effectively infinite scalability. You can do time travel, versioning, zero copy cloning, and you can also offer Snowflake in a consumption-based model where you just pay by the minute or pay by the hour, so you don't have to pre-buy a whole bunch of licenses and a whole bunch of hardware. Okay, so there's real business value to those features. And even though when Snowflake was first created, people thought the chances of survival are very, very slim. The fact that they had innovated architecturally and actually built a lot of what they do on top of immutable data structures, so connection back to theory allowed them to solve a lot of really practical, important problems. Okay, and then the third criteria is that at the paradigm level, we're compatible with these data clouds, with systems like Snowflake and BigQuery, because we're relational, they're relational. Most of sort of the operational data for most enterprises is stored in tables or JSON documents, okay? And so being able to sort of operate in the same paradigm means that you don't have to translate data from a tabular relational representation to a navigational representation or pointer-based representation or tensor-based representation or thinking about things imperatively and procedurally and so on. Okay, so that's sort of what we mean by coprocessor. Okay, at this point, there's usually a bit of enthusiasm in the room, but there's a little bit of like, is this for real? Are you pulling a fast one? Okay, so then the third thing I try to explain to folks is, well, what do we mean by relational knowledge graph? Many of you will have heard the term knowledge graph, but we've sort of prefixed it with relational. And I'm going to define it as a relational knowledge graph is a relational database organized in graph normal form with relevant domain knowledge described in an expressive relational logic or relational language. Okay, so when Ted Codd, a theory person, first published on this, the original relational database work didn't really specify SQL or specify a specific way of organizing data. And as people started to build systems based on those ideas, they started making compromises because we didn't have all the algorithms we needed or all the data structures we needed to make things work. And so typically, historically, data in relational databases has been stored in a denormalized manner because joins are expensive and I'll create 50 column tables because then I don't have to reassemble or rejoin those things together because joins are expensive. And one of the big knocks on relational databases was performance. Anyways, graph normal form is sort of like the ultimate normal form. It is atomic and irreducible and gives us the ability, though, to represent data in a variety of ways and tables and graphs and so on. Okay, so I'll touch on that very briefly. So how do we represent graphs in a relational database? Well, graphs can be represented with pointers or with matrices and so on, but obviously a graph is also representable as a two-column relation connecting, where every edge is just a row in that relation or in that table. So here, a quick example is if I have a SQL table like this, I can think of the table as a modularity construct that groups together a graph that connects an order to a customer or an order to a date or an order to a price, okay? So tables are just groupings of these sort of graphs that maybe share a common key or something, okay? I can also represent JSON documents this way. I won't get into that today. JSON documents can be represented actually a couple different ways. One is sort of as a path to a value, or two, you can think of JSON documents as like being pre-joined relational data, and we just want to re-normalize it into graph normal form. And of course, I can represent tensors and vectors and matrices this way as well. So a vector is also a binary relation with sort of an implicit index that's the offset into the vector, row 1, row 2, row 3, and here are the values. A matrix is row column value, tensor, n-dimensional, you get the idea. And of course, you can express operations in linear algebra in a fairly straightforward way. And here's even a SQL implementation of matrix multiplication where you're selecting the rows from A, the columns from B, you're multiplying the values of A and B, and then you're joining the columns from A with the rows from B and so on. Okay, so these worlds tend to sort of be separate worlds for people, and we're trying to bring them all into one context. Okay, so I don't have time to get into it, but quickly I will just sort of sketch out. When people move data from 17,500 SQL databases into Snowflake, they're very happy because now it's one-stop shop to go and get all your BI and your data scientists or whatever. But then they also realize you have 17,500 data models and schemas and so on. It's still a kind of a bit of a mess. So what the industry is moving towards is sort of building a semantic layer on top of the 17,500 or thousands of data silos so that you can come up with sort of a common schema or common ontology for speaking about that business. The other thing they realize when they move all that data into Snowflake is that they have, that data is usually coming from databases that drive applications, and the application logic doesn't move. So if you're computing gross margin or you're computing somebody's age from their date of birth, you might have date of birth in a table, but age is typically written in Java or COBOL or something, right? So people want to move semantics that are currently represented procedurally into this world so that they don't have to continually re-implement and rewrite semantics. Lots of good reasons for this around reusability, shareability. Semantics are more compact, they're more optimizable, they're more portable. Lots of different approaches to doing that, different languages. But anyways, I'll close on this. So the idea here is that we plug into your data cloud of choice, today Snowflake, and we add support for workloads that are not normally supported, that allow you to express more interesting, more intelligent semantics and put them all in one place, sort of in a declarative foundation, as opposed to having to deal with the fragmentation and the mix of modeling techniques and programming techniques and all of that stuff. All right, so with that, I'll stop. Thanks.
Quick question, if someone has one. So, here from our next speaker.